This is Dreamtime Science, where we paint the canvas of your dreams with the soft brushstrokes of scientific wonder. Together we'll explore the mysteries that dance at the edge of consciousness. You know what's fascinating? I've been thinking a lot about why so many things around us spin, like the Earth turning on its axis or a simple top twirling on a table. There's something quietly remarkable about how rotation shapes everything from the tiniest atoms to the vastness of galaxies, and I can't wait to share some of those gentle secrets with you tonight. Should these dreamy explorations accompany your journey to sleep, a gentle like or subscription would be deeply appreciated. What questions about our universe keep you wonderfully curious? Before we begin, create your sanctuary, nestle into your chosen spot, let your muscles soften, and allow your breath to find its natural rhythm. In the hush of night, as the world lies cloaked in shadow, and the only sound is the distant hush of wind, the mind drifts to the heavens. Beyond the modest boundary of our own blue planet, an endless ballet unfolds, its choreography old as time and as inexorable as the pull of gravity itself. This is the great cosmic dance, an eternal waltz of galaxies, stars, and planets, spinning and spiraling with a silent, ceaseless grace. Long before telescopes or equations, our ancestors gazed upward, entranced by the slow, stately arc of the stars across the sky. The earliest civilizations, from the river banks of Mesopotamia to the high plateaus of Mesoamerica, watched the heavens and wove their stories around the apparent motion of celestial lights. They saw the stars wheel above them, predictably returning night after night, season after season. The sky itself appeared to turn, as if the entire dome of the heavens were a colossal wheel spinning around a fixed axis. In their myths, the universe was often imagined as a great spinning disk. The Norse spoke of Yggdrasil, the world tree, whose branches and roots bound together the cosmos, and whose axis was the spine around which the heavens revolved. In ancient India, the celestial sphere was likened to a chariot wheel, its spokes marking the passage of time and fate. The Greeks, too, envisioned the heavens as a set of crystal spheres, each turning in harmonious motion, carrying the planets and stars in their eternal circuit. But it was not only in myth that the spinning cosmos found its place. Even in the modern age, the idea of rotation, the spinning of worlds and the whirling of galaxies, has captured the imagination of artists, writers, and dreamers. Science fiction, in particular, has made the spinning of the universe both a spectacle and a symbol. Think of the iconic image of the spinning space station in 2001, A Space Odyssey, its rotation generating a gentle gravity for its inhabitants. Or the spiraling galaxies in the opening frames of countless interstellar epics, each swirl a promise of adventure and mystery. All of these stories, these visions and dreams, are rooted in a simple, ancient truth. Spin is everywhere in the universe. From the smallest grain of cosmic dust to the largest galaxy cluster, rotation is one of the fundamental movements of matter. The universe, it seems, cannot help but turn. But why do things spin? To answer this, we must begin not with the stars themselves, but with the very birth of the cosmos. Some 13 billion years ago, in the cosmic dawn that physicists call the Big Bang, the universe began as a hot, dense soup of energy and particles. Out of this roiling chaos, the first atoms formed, and with them the earliest seeds of structure. Even in those primordial moments, small fluctuations, tiny ripples of density, set the stage for the future. Where matter was just a fraction denser, gravity tugged a little harder, and over time these regions began to collapse under their own weight. But collapse in the universe is never simple. For even the tiniest irregularity in the distribution of mass, an atom drifting a little to one side, a slight asymmetry in the swirl of primordial energy, means that as clouds of gas and dust fell together, they also began to spin. This is the principle of angular momentum, a concept as fundamental to physics as the rising of the sun is to the rhythm of the day. Imagine a figure skater on ice. As she spins with her arms outstretched, her rotation is steady and slow. But when she draws her arms in, she spins faster, her body whirling in a blur. The same principle holds in the cosmic arena. A vast cloud of gas and dust, light years across, may begin its existence almost motionless, with only the faintest hint of rotation. But as gravity pulls it inward, as it collapses, any small spin is amplified. The cloud whirls faster and faster, its rotation becoming more pronounced as it shrinks. This is the humble origin of all cosmic rotation. Stars, planets, even galaxies themselves. Their spin is the legacy of ancient, subtle motions, preserved and magnified by the laws of physics. Consider our own solar system. The Sun, a massive ball of burning hydrogen, spins on its axis, completing a rotation roughly every 25 days at its equator. Around it, the planets revolve in a broad, flat disk, each spinning in its own rhythm. Jupiter, the giant, whirls around in less than 10 hours, its vast storm spun up by the planet's rapid rotation. Saturn, with its luminous rings, turns only a little slower. Even the smaller worlds, Mars, Venus, the rocky Earth, partake in this dance, each with its own tempo and tilt. The reason for this coordinated motion lies in their shared origin. 4.5 billion years ago, the solar system formed from a collapsing cloud of gas and dust, its material drawn together by gravity. As the cloud shrank, its rotation sped up, flattening into a disk, a cosmic pancake from which the sun and planets were born. The spin of each world is a fossil, a record of the swirling motions of that ancient nebula. Yet the universe is not content with merely spinning planets and stars. On a far grander scale, galaxies themselves are caught in the throes of rotation. The graceful spirals we see in distant galaxies, their arms curving outward like the petals of a cosmic rose, are shaped by the rotation of billions of stars, gas clouds, and unseen dark matter. The Milky Way, our own galactic home, is a disk more than 100,000 light-years across, turning majestically about its center. Our solar system, tucked away in one of its spiral arms, orbits the galactic core at some 220 kilometers per second, completing a circuit every 230 million years. It is a journey so vast, so slow, that the rise and fall of continents on Earth are but fleeting moments in a single galactic year. And yet, to the human mind, this cosmic spinning is not just a fact to be measured. It is a source of wonder, a metaphor for the invisible forces that bind the universe together. In the whirling of galaxies, we see echoes of our own lives, the cycles of birth and decay, the turning of seasons, the rhythm of days and nights. It is little surprise, then, that science fiction and popular culture have seized upon the idea of spinning worlds and galaxies as both a visual motif and a narrative device. In the pulsing lights of distant stars, we find the promise of time travel and interstellar adventure. In the rotation of planets, we imagine alien days and nights, strange climates, and exotic skies. In the stories of Asimov and Clarke, of Le Guin and Bradbury, rotation is often the key to survival and exploration. Space stations spin to create artificial gravity, their inhabitants walking on curved floors that mimic the pull of Earth. Ships hurtle through the void, their engines imparting a gentle spin to keep their crews anchored. Whole worlds are imagined as rotating habitats, giant cylinders or toruses, where day and night are generated by the play of light and shadow, the balance of centrifugal force and gravity. Even in music, the spinning of the cosmos has found its echo, the music of the spheres, a phrase from the ancient Greeks, conjuring the idea that the planets and stars produce a celestial harmony as they turn. In truth, the universe is silent. Its music is one of motion and mathematics, of patterns and orbits. But in that silence lies a profound resonance, a sense of order and beauty that has inspired poets and scientists alike. Beneath the surface of these cultural echoes, however, lies the deeper, immutable law. Angular momentum, the tendency of spinning objects to maintain their motion, is conserved throughout the universe. Once set in motion, a spinning body will keep rotating unless acted upon by an external force. This is why the planets and stars, once spun up by their birth throes, continue their dance for billions of years. The friction of space is vanishingly small. Nothing stands in the way of their eternal pirouette. Yet, rotation does not always remain unchanged. Over cosmic timescales, interactions between bodies, collisions, tidal forces, the gravitational tug of neighbors, can steal or add angular momentum. When two galaxies pass close by, their mutual gravity can twist and warp their shapes, flinging streams of stars and gas into space, sometimes coalescing into new, smaller galaxies. When a planet orbits too close to its star or a massive moon, tidal forces can slow its spin or lock it into a synchronous rotation, so one side always faces its partner, as the moon does to the Earth. Still, the underlying principle endures. Rotation is not a passing phenomenon, but a fundamental property of matter in motion. It arises spontaneously from the birth of stars and worlds, and persists across the eons, shaping the very architecture of the universe. As our understanding has grown, so too has our ability to visualize and measure this cosmic spinning. Modern telescopes, peering deep into the night, reveal the swirling arms of distant galaxies, each a masterpiece of rotational symmetry. Radio observatories track the rapid spin of pulsars, collapsed stars no larger than a city, spinning hundreds of times a second, their beams of energy sweeping across space like cosmic lighthouses. Closer to home, spacecraft have visited the spinning worlds of our solar system, mapping their surfaces, measuring their days and nights. The Voyager probes, now drifting in the interstellar dark, once captured images of Jupiter's roiling storms, Saturn's whirling rings, Uranus and Neptune's tilted spinning forms. Each discovery a testament to the omnipresence of rotation, each image a snapshot of the cosmic dance. And so, as we lie beneath the turning sky, we are not merely witnesses to this grand ballet, we are participants. The very ground beneath our feet spins eastward at hundreds of meters per second, carrying us from night to day and back again. The Earth itself orbits the Sun, riding the wave of its ancient angular momentum, and the Sun in turn wheels about the galactic core. We ourselves are part of a spinning lineage, connected by invisible threads to the birth of the cosmos. What then is the significance of all this turning? Is it merely a quirk of physics, a relic of the universe's uneven beginnings? Or does it point to something deeper, a principle of unity, a universal rhythm that joins the smallest atom to the largest galaxy? The answer, perhaps, lies in the interplay of order and chaos, of symmetry and disruption. For while the universe is filled with spinning bodies, no two are quite alike. Each world, each star, each galaxy carries the imprint of its own unique history, the collisions it has endured, the companions it has danced with, the forces that have shaped its path. And yet, in the broad sweep of the cosmos, a pattern emerges, a sense of connectedness, of shared motion. The dance of the galaxies is not random, but governed by laws as simple as they are profound. The same physics that governs a child's spinning top guides the rotation of worlds and suns, binding the universe together in a web of motion and balance. As we drift into sleep, let the mind linger on the image of spinning galaxies, their arms stretched wide in the dark. Let the imagination wander among the stars, tracing the invisible lines of angular momentum that tie us to the birth of all things. For in this endless turning there is both comfort and mystery, a reminder that the universe is not static, but alive with motion, forever dancing to the silent music of its own making. And yet in the heart of this cosmic waltz, there are questions still to be asked. How does the act of spinning shape the lives of stars and planets? What secrets are hidden in the whirling storms of Jupiter or the tilted axis of Uranus? What happens when the dance of rotation collides with the forces of gravity, magnetism, and time itself? The answers, as ever, lie just beyond the next turning of the heavens, awaiting discovery in the quiet moments before dawn. Beneath the gentle hush of night, when the world seems still and the mind is unmoored from daily demands, the secret choreography of the universe continues in silent, ceaseless motion. It is in these hours, when shadows grow long and quiet, that the mind finds space to ponder the deeper mechanics of movement, those elegant, invisible forces that govern the turning of wheels, the spinning of planets, and the joyful whirl of a child's toy set dancing across the floor. To truly appreciate the spinning world and all things that rotate within it, we must slip into the company of two steadfast partners, forever entwined in a cosmic waltz, torque and inertia. Their interplay is the pulse of rotation, the secret behind the persistence of the spinning top, the balance of a figure skater, and the stately pirouette of the earth itself. Tonight, let us draw closer to this intricate dance and trace its steps across scales both humble and grand. Begin then with a memory. Somewhere in your past, perhaps, you have felt the mysterious resistance of a merry-go-round as you tried to set it spinning. The old metal disc, dappled with sunlight and the laughter of friends, would not yield easily to your first push. It demanded effort, a force applied at just the right point, with just the right direction, a force we call torque. In that moment, your hands were not merely shoving, they were summoning a twist, coaxing the merry-go-round to abandon stillness for motion. Torque, in the language of physics, is the rotational cousin of force. Where force pushes or pulls in a straight line, torque twists and turns, urging objects to spin about an axis. It is defined not just by how hard you push, but by where you push and in which direction. Imagine a wrench gripping a stubborn bolt. A gentle tap near the center yields little, but a strong push at the end of the handle multiplies your effort, making the bolt yield with a satisfying turn. The further from the axis you apply your force, the greater the torque, a principle that underpins not only tools and machines, but the very architecture of the cosmos. The measure of torque is a simple product, the magnitude of the force, multiplied by the distance from the axis of rotation, and multiplied again by the sine of the angle between the force and the lever arm. In most cases, the greatest effect is achieved when the force is applied at a right angle to the lever, maximizing that twisting urge. This is why doors open so easily when you push at the handle, far from the hinges, but resist your efforts if you press too close to the pivot point. But torque alone does not guarantee motion. There is always another player in this drama, a stubbornness, a reluctance to change, built into the very matter of things. This is inertia, the property by which objects resist alteration of their state. In the linear world, inertia is described by mass. The greater the mass, the harder it is to start or stop an object's motion. In the realm of rotation, inertia takes on a new and subtle form, the moment of inertia. The moment of inertia is the rotational equivalent of mass, but it is shaped not only by how much material an object contains, but by how that material is distributed relative to the axis of rotation. Picture two wheels, one a solid disk, the other a ring of equal mass. Spin them both, and you will discover a curious fact. The ring resists acceleration and deceleration more fiercely than the disk, even though they weigh the same. The reason lies in the distance of the mass from the axis. The farther the mass, the greater the moment of inertia, and the more stubbornly the wheel clings to its current state of motion. This principle explains the peculiar grace of the figure skater, who, arms extended, spins slowly at the center of the rink. As she draws her arms inward, tucking them close to her body, she spins faster and faster, her moment of inertia shrinking even as her angular momentum remains the same. The universe, ever thrifty, refuses to waste rotational energy. The product of moment of inertia and angular velocity, angular momentum, remains constant in the absence of external torque. Thus, the skater's pirouette becomes a vivid lesson in conservation, a testament to the quiet laws that shape our world. But let us return to the merry-go-round, now spinning freely under the fading light. To change its speed, to bring it to a halt, or to make it spin faster, requires torque, and the effect of that torque is governed by the moment of inertia. A light, narrow disk responds quickly to your push, while a heavy, broad one is sluggish, requiring greater effort. This interplay governs all rotational motion, from the smallest gyroscope to the most massive galaxies. Consider the spinning top, its slender stem balanced delicately on a point, its motion a blur of color and sound. When you snap your fingers against it, you are imparting torque, setting it in motion. The shape of the top, the distribution of its mass, determines how long it will spin, how gracefully it will precess and wobble as friction slowly drains its energy. The top's moment of inertia, calculated from the sum of each tiny piece of mass multiplied by the square of its distance from the axis, defines its resistance to changes in spin. A top with more mass concentrated at the rim will stubbornly maintain its rotation, spinning for long, mesmerizing minutes. One with mass near the center will spin more quickly, but come to rest sooner. The same principles scale up, magnified to cosmic proportions. Take the Earth, for instance, whirling on its axis with steady, ancient rhythm. The planet's mass is distributed in a roughly spherical shape, not perfectly uniform, with dense iron at the core and lighter rock above. The moment of inertia of the Earth is a vast sum of all these parts, each contributing to the planet's resistance to changes in its rotation. It is this inertia that keeps the Earth turning with such unyielding regularity day after day, year after year. Yet even the Earth is not immune to torque. The Moon's gravity tugs at our planet, raising tides in the oceans and over millennia gradually slowing the Earth's spin. This tidal torque acts relentlessly, exchanging angular momentum between the Earth and the Moon, causing the Moon to spiral ever farther away as our days lengthen imperceptibly. Here, on a stage vast beyond imagining, torque and inertia engage in a dance measured not in seconds, but in eons. In the quiet corners of the laboratory, the tango of torque and inertia unfolds in miniature. A bicycle wheel, spinning freely on its axle, resists any attempt to change the direction of its rotation. Try to tilt the axle, and you feel a force pushing back, a phenomenon known as gyroscopic precession. The wheel's spinning mass, its moment of inertia, and the torque you apply conspire to produce motion perpendicular to your push. This effect, subtle yet unmistakable, is harnessed in the design of gyroscopes and in the stability of bicycles, in the guidance systems of spacecraft and the navigation of ships across the open sea. Even in the world of atoms, the dance persists. Tiny particles possess angular momentum, quantized in discrete steps, their spins governed by the same mathematical rules that dictate the motion of planets and stars. The electron, spinning within its cloud of probability, carries a miniature moment of inertia, its behavior echoing the familiar laws of the macroscopic world in the strange, probabilistic language of quantum mechanics. Everywhere, the story is the same. Torque is the agent of change, the initiator of motion, while inertia is the guardian of continuity, the keeper of the status quo. Together, they determine not only how things begin to spin, but how they persist or falter, how they respond to the countless invisible nudges and tugs that fill the universe. Turn now to a humble demonstration, a child at play with a wooden seesaw. The plank, balanced atop its pivot, responds to weight applied at different points. Push at the end, and the seesaw tips easily. Press near the center, and the effect is slight. The seesaw's turning is a question of torque. the product of force and distance from the fulcrum. Its resistance to being tipped is a matter of inertia, of how its mass is distributed about the pivot. The same principles guide the engineer designing bridges and cranes, the architect calculating the stability of a tower, the craftsman selecting the shape of a spinning pot on a wheel. In the silence of the night, even as you lie still, the world around you is alive with rotation. The ceiling fan above, its blades slicing through the air, obeys the same dictates. The motor supplies torque, overcoming the inertia of the blades to set them whirring. The planets overhead, spinning on their axes and orbiting the sun, are governed by the same equations that describe the turning of a potter's wheel or the twirling of a dancer. And yet, there are mysteries and subtleties still to uncover. The interplay of torque and inertia is not always straightforward. Friction, air resistance, and internal dissipation can sap energy from a system, slowing its motion and complicating the dance. In rigid bodies, mass may be fixed, but in fluids or deformable objects, the distribution of mass can change, altering the moment of inertia in the midst of motion. The dynamics of rotating systems can be astonishingly complex, giving rise to chaotic movement, wobbling, and even sudden reversals. Somewhere in the universe, a neutron star spins hundreds of times each second, its mass compressed into a sphere only a few kilometers across. Its moment of inertia is enormous, its rotation so stable that it serves as a cosmic clock, broadcasting regular pulses of radio waves across the galaxy. Elsewhere, a collapsing cloud of gas in a distant nebula acquires a tiny twist, a whisper of torque amplified by gravity and the conservation of angular momentum, setting a new star and its planets in motion. In every spinning thing, from the mundane to the magnificent, the tangled tango of torque and inertia persists. It is a dance that shapes the sweep of galaxies, the rhythm of tides, and the gentle twirl of autumn leaves caught in a breeze. The laws are patient, impartial, and universal. They do not tire, do not sleep, but govern all things with unwavering certainty. Tonight, as your thoughts drift and begin to settle, consider the quiet persistence of these principles, the way they underlie every turning, every tumbling, every subtle shift. The world is never truly still. Beneath apparent calm, the wheels of physics turn, weaving the fabric of existence from countless rotations, small and large. And as the night deepens, the story of rotation continues, drawing us onward toward still more intricate dances, toward the peculiar secrets of spinning bodies under new and strange conditions, the peculiarities that arise when rotation meets relativity, or when the simple laws of torque and inertia are bent and reshaped by the demands of speed and gravity. The universe, it seems, is never content with simple circles. There are always new steps to learn, new rhythms to follow in the great, unending dance. In the hush of early morning, before the world stirs, a sense of quiet anticipation hangs in the air, a stillness that is, in truth, never truly still. For even as the dew settles and shadows grow long, our planet is sweeping through space, twirling on its axis in a stately pirouette that has continued for billions of years. Yet for the vast majority of human history, this subtle spin was hidden, its presence so constant and so immense that it was simply taken for granted, or indeed not suspected at all. To truly grasp the turning of the world, to measure it, to prove it, this would require patience, ingenuity, and the slow unfolding of scientific curiosity across centuries. The earliest humans, gazing up at the slow procession of stars, must have wondered, do the heavens move, or does the earth itself turn? The question lingered, unresolved, for millennia. In antiquity, the notion of a spinning earth was considered fanciful, even absurd by many. After all, if the ground beneath our feet truly whirled at dizzying speed, would not everything be thrown violently outward? Would birds not be left behind in the rush? It would take not only new tools, but a revolution in thought to untangle the truth from the comforting illusion of stillness. The journey toward understanding rotation is, in many ways, a journey through the very heart of science, through the delicate interplay of observation, experiment, mathematics, and imagination. With each step, new instruments emerged, conjured by restless minds seeking to measure the imperceptible, to coax secrets from the quiet whir of the cosmos. The tale of unraveling spin is woven from the threads of mechanical ingenuity and philosophical daring, from the steady ticking of clockwork to the silent, invisible tug of gravity itself. We begin, perhaps, with the pendulum, a device as simple as a child's toy and as profound as the stars. A weight suspended on a long cord, allowed to swing freely, back and forth, tracing a graceful arc through the air. For centuries, pendulums served as timekeepers, their regular oscillations marking out the rhythm of days and nights. Yet in the hands of the French physicist Léon Foucault, the pendulum became a messenger of cosmic truths. Imagine a quiet chamber in the heart of Paris. The year is 1851. In the great dome of the Panthéon, a heavy brass bob, 28 kilograms of polished metal, hangs from a wire 67 meters long. Foucault's pendulum, set in motion with a gentle push, swings back and forth, almost hypnotic in its measured grace. At first, it seems little more than an elegant curiosity. But as the minutes pass, something peculiar becomes evident. The plane of the pendulum's swing appears to rotate, ever so slowly, relative to the floor below. In reality, this slow turning is not due to any force acting on the pendulum itself, but to the motion of the Earth beneath it. As the planet spins, the pendulum's swing maintains its orientation in space, like a cosmic compass, steadfastly pointing the way. The effect is subtle. In Paris, the plane of swing completes a full rotation in about 32 hours. Closer to the poles, the effect is more pronounced. At the North or South Pole, the rotation matches the period of the Earth itself, one full turn every 24 hours. Here, at last, was visible, tangible proof that the ground beneath our feet is not the steady anchor we imagine, but a moving stage in a grand celestial dance. Foucault's experiment was an act of both simplicity and genius. It required no astronomical instruments, no distant stars, only a well-made pendulum and a watchful eye. Yet its implications were profound, settling a debate that had echoed since the days of Copernicus and Galileo. The pendulum became a symbol of scientific triumph, a reminder that with the right tools, even the subtlest truths could be brought to light. But the pendulum, for all its elegance, is only one of the many instruments devised to probe the mysteries of rotation. As our understanding deepened, so too did our ingenuity. The gyroscope, for instance, is a marvel of spinning motion, essentially a wheel mounted in such a way that it can spin freely about its axis, regardless of how its base is moved. When set spinning, the gyroscope resists changes to the orientation of its axis, a phenomenon known as conservation of angular momentum. To see a gyroscope in action is to witness the strange and beautiful stubbornness of nature. A spinning top, its axis tilted, does not fall. Instead, it precesses, tracing a slow circle in the air. This resistance to change is the same principle that keeps a bicycle upright when in motion, or that allows spacecraft to orient themselves in the frictionless void of space. The gyroscope's secrets were unraveled in the 19th century as engineers and physicists sought to harness its stability for navigation. In the days before GPS, ships and airplanes relied on gyroscopic compasses to maintain their course, even when storms and waves conspired to turn them astray. Inside these instruments, tiny wheels spun at thousands of revolutions per minute. their angular momentum anchoring them to an invisible reference frame, the distant stars, the silent background of the universe. And yet, rotation is not always so easily tamed or measured. The Earth's spin gives rise to phenomena that are at once familiar and mysterious: the trade winds, the paths of hurricanes, the swirling of ocean currents. These are all shaped by the Coriolis effect, a subtle consequence of rotating frames of reference. To those living on the surface, the effect is invisible, yet its fingerprints are everywhere. A cannonball fired northward will drift slightly east, not because of any force acting directly upon it, but because the ground beneath it is spinning at a different speed. The same effect steers the great rivers of wind that encircle the planet, shaping weather and climate in ways that only careful measurement can reveal. To study these effects, scientists turn to ever more refined tools: anemometers to measure the speed of wind, barometers to track changes in pressure, and eventually satellites to watch the world from above. In laboratories, delicate experiments were devised to test the tiny deflections predicted by theory. Spinning disks, rotating tanks of water, and even the careful tracking of falling objects all became part of the arsenal. Each experiment a small step toward understanding the true nature of our spinning home. As the 20th century dawned, a new revolution in physics swept across the world, one that would rewrite our understanding of space, time, and rotation itself. At its heart was Albert Einstein, whose theories of relativity changed forever the way we see the cosmos. In Newton's universe, rotation was simple: a body spun, its motion governed by clear, unchanging laws. But Einstein saw deeper, recognizing that space and time themselves could curve and twist, responding to the presence of mass and energy. In Einstein's general theory of relativity, rotation took on new and astonishing forms. No longer was it enough to speak of spinning planets or tumbling asteroids. Now, the very fabric of space-time could be set in motion, dragged along by the rotation of massive bodies. This phenomenon, known as frame dragging or the lens-thirring effect, predicted that a spinning planet would twist the space around it ever so slightly, like a spoon swirling honey in a teacup. Testing this prediction required precision beyond anything previously attempted. In the early 21st century, NASA launched the Gravity Probe B satellite, a gleaming cylinder packed with some of the most perfect spheres ever created. These gyroscopes, spinning in the vacuum of space, were shielded from every conceivable disturbance: stray magnetic fields, faint breezes of solar wind, the tiniest vibrations. Over the course of a year, scientists watched as the axes of these gyroscopes shifted by fractions of a degree, just as relativity predicted, a silent nod from the universe to the correctness of Einstein's vision. But even as our tools grow ever more refined, the quest to understand rotation continues to inspire new experiments, new questions. In the laboratories of today, scientists trap atoms in beams of laser light, spinning them to probe the quantum nature of angular momentum. Astronomers peer into the depths of space, watching the spin of neutron stars and the whirling disks of gas around black holes. Each observation, each measurement adds a thread to the tapestry of knowledge, revealing ever more intricate patterns in the fabric of motion. Consider for a moment the humble spinning coin, a child's amusement, and yet a microcosm of rotational physics. As the coin spins, it wobbles, precesses, and eventually falls, the interplay of friction, angular momentum, and gravity playing out in miniature. Physicists study such simple systems to unravel the complex mathematics that govern all spinning bodies, from the smallest molecule to the largest galaxy. The equations that describe their motion, Euler's equations, the laws of conservation, the symmetries of space, are written in the language of mathematics, yet their meaning is etched into the very turning of the world. The history of studying rotation is filled with moments of triumph and frustration, of ingenious experiments and unexpected discoveries. From Galileo's inclined planes, rolling balls down smooth tracks to measure the acceleration of gravity, to the spinning flywheels and balance wheels that kept the earliest clocks ticking, each advance was built upon the patient work of countless observers, tinkerers, and dreamers. In the quiet of laboratories and the open air of observatories, these pioneers sought to measure the unmeasurable, to make visible the hidden forces that shape our world. And so, through pendulums and gyroscopes, through satellites and spinning coins, we have come to see rotation not as a mere curiosity, but as a fundamental feature of the universe. It is written into the laws that govern atoms and stars, into the swirling of clouds and the turning of seasons. It shapes the paths of planets and the dance of galaxies, a silent, ceaseless rhythm that underlies all of creation. Yet for all that we have learned, for all the cleverness of our instruments and the elegance of our theories, rotation still holds mysteries yet unsolved. The quantum world, with its strange rules and hidden symmetries, hints at new forms of spin, particles that twirl in ways that defy our everyday intuition. In the hearts of neutron stars, matter spins at unimaginable rates, squeezed to densities that boggle the mind. And in the earliest moments of the universe, perhaps, a primordial spin set the cosmos itself in motion, a first turning that echoes down through time. With each new tool, each new experiment, we peel back another layer of the spinning world, glimpsing patterns both familiar and strange. Our quest is far from over. The story of rotation continues to unfold, inviting us onward, ever deeper into the heart of motion. As night deepens and the stars wheel silently overhead, one cannot help but wonder what secrets still lie hidden in the whir and whisper of the turning earth, waiting for the next curious mind to listen, to watch, to devise a new way of seeing. And so, as the pendulum swings and the gyroscope holds its silent vigil, our gaze turns outward and inward, seeking patterns in the stars and in the flicker of atoms alike. The journey through rotation is not merely a tale of tools and trials, but of triumphs yet to come, discoveries yet unmade. The world turns, and with it our understanding, ever spinning onward into the waiting dark. In that quiet, unresolved motion, the promise of revelation lingers, subtle, persistent, and endlessly alluring. There is a quiet, persistent hum beneath the fabric of reality, a tremor that is more than vibration, more subtle than the pulse of energy in a wire. It is spin, the gentle, ceaseless turning that threads through the cosmos, from the smallest particles to the grandest galaxies. If you listen, not with your ears, but with the mind's inner ear, you may catch the faint echo of this hidden rotation, a signature imprinted on matter and motion, an unbroken thread that links the physical to the philosophical, the scientific to the existential. In the hush of night, when the world grows still and the boundaries between the self and the cosmos blur, one may reflect on the deep, almost mystical meaning of spin. Spin is not simply a property of things, it is a mode of being. It is, in the language of quantum mechanics, an intrinsic angular momentum, a quantum number, a direction, a binary whisper that underlies the ways particles interact, repel, attract, and sometimes dance together in composite symmetry. But step back, and the narrative unfolds into the macroscopic, the Earth rotating beneath our feet, the slow pirouette of the moon around our planet, the sun's broad, stately revolution, the star fields swirling in the arms of the Milky Way. What does it mean to live in a universe where nothing is truly at rest, where stillness is a fleeting illusion, and the default state is motion, circular, perpetual, inescapable? The ancient philosophers, gazing up at the heavens, saw the circles traced by planets and stars, and interpreted them as signs of perfection, of harmonious order. The circle, so they believed, was the most divine of forms, embodying eternity, wholeness, and the absence of beginning or end. Aristotle imagined the celestial spheres turning in unending cycles, moved by an unmoved mover, an entity beyond time and change. Yet as the centuries rolled onward, the dance of the heavens lost none of its power to provoke questions. Galileo, with his crude telescope, beheld the spinning of Jupiter's moons and the shifting phases of Venus. Newton, with cool abstraction, gave us the laws that govern rotation and revolution, but even he could not quite explain why the universe should be so wedded to the idea of motion. Why should inertia exist? Why should a planet, once set spinning, continue to spin forever unless acted upon by a force? The laws of physics are descriptive, not prescriptive. They tell us how, not why. Let us linger for a moment with this why. Why spin and not stasis? Why do the building blocks of reality bristle with angular momentum? Why do electrons whirl with a half-integer spin? Why do protons rotate? Why do entire galaxies spiral? Might the universe, at its most fundamental level, abhor the idea of absolute stillness? Could it be that rotation is a kind of resistance to nothingness, a rebellion against the void? There is a profound metaphysical resonance in this idea. To spin is to exist in time, to mark the passage from one moment to the next. A spinning top, once wound and set upon the table, seems to defy gravity's downward pull. Its axis, stable for a few seconds or minutes, resists the chaos of falling. In that brief interval, it is more than a toy. It is a metaphor for persistence amid entropy, for the way forms endure and cohere in a universe always tending toward disorder. The physicists who peer into the quantum realm find that spin is not rotation in the classical sense. An electron's spin is not the whirling of a tiny sphere, but an abstract property, an arrow in an invisible space, a duality that governs how it interacts with magnetic fields. Yet even here, the language of spin persists, as if our minds cannot help but clothe the invisible in the garments of the tangible. The very word spin is a kind of poetic concession, an admission that the universe's deepest truths may be forever out of reach, describable only by analogy and metaphor. It is no accident that human culture is saturated with images of spinning and turning. The wheel, one of our earliest inventions, became the fulcrum of civilization, transforming transport, grinding grain, shaping pottery. The cycle of the seasons, the rhythm of day and night, the oscillation of the pendulum, all are echoes of the grand rotation that envelops us. Dervishes whirl in sacred ecstasy, dancers spin in joy, planets wheel in the vault of space. The act of spinning is at once playful and profound, a microcosm of cosmic order. In philosophical terms, spin challenges the notion of identity and change. Heraclitus famously declared that one cannot step into the same river twice. Everything flows, everything changes. Yet the act of spinning is a paradox. The form persists even as the position changes moment by moment. The spinning coin blurs into a disk, its heads and tails indistinguishable in the motion, a superposition, if you will, of two states. Only when the spin ceases does the outcome crystallize, the ambiguity resolve. In quantum mechanics, this is more than a metaphor. It is the essence of measurement, of collapse, of the transition from possibility to actuality. There is a further mystery, subtle and persistent, that haunts the concept of rotation. In a universe governed by the laws of relativity, motion is always relative, save for rotation. If two astronauts, far out in deep space, float in identical spheres, they cannot detect uniform motion. Each sees the other as stationary. But if one sphere spins while the other remains at rest, the spinning astronaut feels the centrifugal force, the pressure against the hull, the sense of being flung outward. Rotation, unlike straight-line motion, is absolute. Einstein wrestled with this fact, as did Mach before him. What is it about spinning that anchors it to the very geometry of space? Is there a preferred frame, a cosmic gyroscope by which all rotation is measured? This question, unresolved, echoes in the corridors of physics. Newton's bucket argument, the surface of water climbing the walls of a spinning bucket, suggests that rotation is not merely relative to nearby objects but to the universe itself, to the sum total of all mass and energy. Mach speculated that inertia and rotation might arise from the gravitational influence of distant stars, the great cosmic backdrop against which all motion is reckoned. In this view, to spin is to be in dialogue with the universe as a whole, to tug against the invisible web of all that exists. Perhaps this is why the image of spinning resonates so deeply in the human psyche. We too are suspended in the vastness, turning on our axis, held in orbit by forces we do not fully comprehend. Our lives are cycles within cycles, the rhythm of breath, the beating of the heart, the turning of generations. Each of us is both the spinner and the spun, the axis and the orbit. In the realm of metaphysics, spin invites us to contemplate the nature of persistence. What does it mean for a thing to endure through time? The spinning top persists not in spite of motion, but because of it. The gyroscope, so long as it turns, resists the pull of gravity, maintains its orientation, points steadfastly toward a distant star. In quantum mechanics, the electron's spin is a kind of fingerprint, unchanging, indelible, a marker of identity. Without spin, there would be no structure, no chemistry, no world as we know it. The Pauli exclusion principle, forbidding two fermions from occupying the same quantum state, arises from the properties of spin. It is spin that builds up the architecture of atoms, that shapes the periodic table, that allows for the complexity of matter. Yet even as spin confers stability, it also embodies change. The act of rotating is a continual transformation, a never-ending departure from one state and arrival at another. The wheel turns, the planet spins, the electron precesses in a magnetic field. Time itself may be thought of as a kind of rotation, a passage, a turning, a movement through successive moments. In the deep language of mathematics, there is a symmetry between rotation in space and translation in time, a hidden kinship that unites the two. This conception of a universe in perpetual rotation is both comforting and unsettling. It suggests that change is the only constant, that persistence is achieved not by resisting motion, but by embracing it. To spin is to endure, to persist amid flux, to carve out a form in the midst of chaos. It is perhaps a lesson for our own lives, a reminder that identity is not static but dynamic, that we are not fixed points but patterns in motion. The mysteries of spin do not end here. In the quantum world, particles with different spins obey different rules. Fermions, with half-integer spin, are solitary, antisocial, refusing to crowd together, while bosons, with integer spin, are gregarious, willing to pile up and act in concert. The entire architecture of reality, the distinction between matter and force, arises from this difference. Why should spin dictate the fundamental symmetries of nature? Why is it written into the laws of physics that the world should be composed of such contrasting characters, some solitary, some communal? There are hints in the mathematics of symmetry and group theory of deeper principles at work. Spin arises from the invariance of physical laws under rotation, the idea that the universe should look the same no matter how you turn your viewpoint. Yet this invariance is not total. Certain particles, when spun through a full circle, do not return to their original state. Only after 2 full rotations do they complete the cycle. This is the strange, counterintuitive property of spin-when-half particles, a property with no classical analogue, a reminder that the quantum world is stranger than any dream. The philosopher may ask, is spin a property of the world or a property of our description of the world? Is it a fact about things or a fact about the way we measure and observe? Does the electron have spin, or is spin the outcome of its interactions with the measuring apparatus, with the rest of the universe? In the crisp language of quantum mechanics, these questions are both meaningful and elusive, pointing toward the limits of what can be known. There is, finally, the question of origin. Why did the universe begin with so much angular momentum? Why do stars and galaxies spin? The prevailing view is that tiny fluctuations in the primordial soup, amplified by gravity, led to the formation of rotating structures. But this only pushes the question further back. Why should the initial conditions have favored rotation at all? Is spin an accident, or is it woven into the very blueprint of being? These are questions for which science as yet has no answer. But perhaps the deeper lesson is this. In a universe where nothing stands still, where every particle and planet and galaxy is caught in the endless act of turning, we too are participants in the cosmic dance. Our thoughts, our dreams, our very selves are spun from the same fabric as the stars and electrons, a fabric that is always in motion, always becoming, never quite at rest. And so, as the night deepens and the stars wheel overhead in their ancient courses, you may find yourself caught up in the quiet wonder of it all. The world turns, the atoms spin, the galaxies spiral, and somewhere in that vast, unending rotation is the space for hope, for meaning, for the enduring mystery that is existence itself. Out beyond the reach of light, in the outermost arms of the galaxy, clouds of gas are still collapsing, still spinning, still giving birth to new suns. The echo of creation persists in every whirl and eddy, in every trembling electron, in every heartbeat. The universe prefers spin over stillness, motion over stasis, change over permanence. And in that eternal turning, there may yet be secrets waiting to be discovered, patterns yet to emerge, symmetries yet to be revealed. Perhaps, if you listen closely, you can almost hear the music of the spheres, the silent, ceaseless song of the universe as it spins itself into being, moment by moment, forever unfinished. As our journey through the swirling dance of spinning worlds drifts to a close, we float gently like a comet tail fading into the hush of space. May the quiet wonder of rotation cradle your thoughts tonight, inviting peaceful dreams to spin softly in your mind. Return soon, dear traveller, for more Dreamtime tales that unravel the cosmos's gentle mysteries.